Bulletproof Radio, a state of high performance.
You're listening to Bulletproof Radio, and I'm Dave Asprey. Thanks for listening. You can find Bulletproof Radio on iTunes, bulletproofexec.com, Podcast One, and everywhere else podcasts can be found. But you probably already knew that because you found this. Today's cool fact of the day is that rain can be more than just water. Rain on Venus or on other planets or maybe even moons can be made of sulfuric acid or even methane. And scientists found a planet 5,000 light years away that has rain made out of iron, which is way cool if you ask me. I don't know what Iron Man has to say about that, but it's got to be cool. Today's guest is a guy I've wanted to interview for a long time, ever since I read his book. And he is a distinguished professor of bioengineering at the University of Washington, where he conducts research on water science at the Pollack Laboratory. He's the executive director of the Institute for Venture Science and the founding editor-in-chief of the journal Water. He's also a founding fellow of the American Institute of Medical and Biological Engineering and a fellow of the American Heart Association and the Biomedical Engineering Association. In other words, he's a complete biohacking badass, although I don't think anyone's ever called him that. And his name is Dr. Gerald Pollack. Jerry, welcome to the show. It's an honor to have you.
Oh, thanks, Dave. I'm really happy to be here. And thanks for the introduction.
You're so welcome. Your book that's probably most famous, at least in the circles where I hang, is called The Fourth Phase of Water, Beyond Solid, Liquid, and Vapor, and it's on Amazon.com. And that's kind of what you're known for, because you're saying, well, why does water do the weird stuff it does that no one has ever explained? And you have that natural sense of curiosity combined with some pretty legitimate scientific research background. But you've also looked at the other book that changed my view on how to hack the human body, which was called Cells, Gels, and the Engines of Life from 2001. This played a pivotal role in me. Oh, look, I think I do have control of my own biology. And you've done some other work on muscles and molecules and all this. And I want to know, how did you get into this stuff? Like you've been doing this for longer than I have, like by a long time. What brought on this level of curiosity and interest in such small things?
Why do you think they're small?
Well, you can't see them is why I think they're small. I think they're fun.
Oh, you mean the molecules? I thought you meant the subjects.
No, the subjects are actually fundamental to everything we are. I mean, how our bodies produce energy, how we turn that energy into motion or thought is fundamental. And almost all of what I do is around tweaking those things. Yeah. But how did you get into those things when you started this research? So little was understood about this stuff. What made you go there?
I was studying muscles and how muscles contract. And what struck me as really weird one day is that when we think of muscles at the molecular level, we consider the proteins and how the proteins interact to produce force. But, muscles contain not only proteins, but also water. In fact, two-thirds of, by volume of our muscles and all other cells too, roughly two-thirds are water. It's actually... It's even more dominant than that if you consider the fraction of molecules that are water molecules. The water molecule is so small that in order to fill that two-thirds by volume, you need to put in a lot of water molecules. And if you do the molecular count, it turns out that more than 99 out of every 100 molecules are water molecules. And it struck me as odd that you could discount 99 out of 100 molecules when trying to figure out how muscles work. There's a theory that prevails now about muscle contraction and how it works, and it dates back about 60 years or more. It was developed by a famous Nobel laureate, a member of the famous Huxley family, Sir Andrew Huxley. And almost everybody follows it. But I found some difficulty with that theory, namely that the evidence didn't fit.
Oops.
And so, oops is right. Oops. Practically every experiment that we did in the laboratory failed to fit the theory. And so we began thinking along other lines. And I began to realize that critical to the entire subject of contraction was the water. The 99 out of 100 molecules did play some role. So then we started to figure out not so much the particular role of water, but of water itself, because water, as you said, is a complicated subject, or it seemed complicated because there are so many anomalies that, in other words, properties of water that we can't predict from any theory. And so I began to scratch my head, and I had a few interesting contacts who, I wouldn't say guided me along the way, but provided some clues that were really instrumental. And then we turned to water. We stopped dealing with muscle contraction, and we began to figure out the properties of water, and we found some real surprises. And those surprises are found especially in the fourth phase of water book, but also some in the cells, gels, and the engines of life book. And I'm flattered that you read them.
Well, cells and gels is one of the reasons that I've become a huge fan of collagen protein, because if you want to make a gel, you've got to have collagen, and I put collagen protein in my coffee, and I think having properly formed collagen is probably really important. And it was your book that made me pay attention to that, and that so the taking the right amino acids to form collagen, or eating bone broth, or any of the ways we get it properly, even though I probably had no collagen in my diet for a very long period of time because I didn't know that would be important. So thanks for that first part there. But the new book blew me away, because let me just ask you a few questions. I know you know the answers, but just because I think our listeners don't. Is water actually liquid? What's your take now that you've studied it?
Well, yes and no. So water is obviously a liquid because you have a glass of water and it behaves like a liquid. But there's another phase of water that we discovered, and that's really in between a liquid and a solid. So most of us have learned that water has three phases. We know there's the solid phase, ice, there's the liquid phase, the one that we put in the glass, and the vapor phase. So that's what we learned, but what we found out is that yet there's a fourth phase that's distinct from all of us. And so it's not a liquid and it's not a solid, but somewhere in between those two. And if you have a little bit of it in your glass of water, which you probably do, you won't really detect the difference. But if you have a lot of it in certain experimental setups, then you can actually measure and find out that this is a highly viscous, it's kind of like honey. In between, honey is not exactly a liquid, but not exactly a solid. And this is the consistency of this fourth phase of water. Well, it has a lot of implications because there's a lot of it around, and it's not a complete surprise because there was a physical chemist more than 100 years ago. His name was Hardy. And he predicted this. He was a colloid chemist, and he said, something even 100 years ago, something doesn't make sense because there are properties of water that are basically not understood. And if you try to understand them in terms of the three common phases, you fail. And he predicted that there's a fourth phase of water. And a number of people actually picked that up over the years. And the fourth phase was kind of called structured water. Yeah. Structured, meaning the molecules are not randomly disposed, but they're actually lined up in some way. And there were actually quite a few such people, the most prominent being Gilbert Ling.
Yes, I have a book
Gilbert
too.
Ling, he's now, I think, 97 years old and still active. And then there was also Albert St. Georgi. And St. Georgi was, you might call him the Nobelist among Nobelists because he was respected and revered. He got his Nobel Prize for discovering vitamin C, and then he worked on muscles and he worked on water. And he's famous for a few quotes. One of them is that life is water dancing to the tune of solids. So he knew that the water was intimately involved in everything that the cell does. And what happened is that people in the early part of the last century, up to the middle part, were deeply interested in water. They got, you might say, deeply immersed in the subject. And then there were two debacles that set the science of water backward. there were two incidents that happened. One of them was called the polywater incident, and the other was called the water memory incident. And I can tell you about these because they're kind of interesting. What the summary of the story is that the people who were studying these two phenomena were roundly criticized by scientists, and so it became the study of water became a kind of scientific joke, and people then became reluctant to pursue it. So the first one, the so-called polywater incident, took place, and it came from the laboratory of a guy named Boris Deryagin. Deryagin was a Russian. He was the most prominent physical chemist in all of Russia. Someone came to his lab and showed him something that got him really excited, and then he pursued it. What happened was that if you evaporate water, so the water is pure, and then condense it again, and condense it into small capillary tubes, little glass tubes or quartz tubes, the water took on very strange characteristics. It was really difficult to freeze it. You couldn't boil it until you reached very high temperature. It was denser than ordinary water, and the people the physical chemists who measured the spectroscopic properties, that is the absorption properties, different wavelengths, found it was really strange. It didn't behave at all as though it were regular water. So this was the time of the Cold War, and the Russians and the West didn't communicate a whole lot, so the papers were written in the Russian language. And when they started to be translated into English, the scientists in the West became really excited about this. And at first, they took up the result, and they really had two choices, because of the political background. One choice was to dismiss it as nonsense, because after all, the Russians are enemies, and how could they do anything meaningful in science? And the other one was to try to pursue it and find something that use the Russian findings as leverage to find something even more important or exciting. It looked as though there was a different phase of water, just as what we're talking about. So it was pursued really actively, and there was a lead article in the journal Science, which is one of the couple of really major journals, and the title was Polywater. Why polywater? Because the water behaved like a polymer. Instead of a collection of individual molecules, it behaved as though the molecules were somehow linked to one another. And because of this linkage, the behavior changed markedly. One group, I believe it was an American group, just a couple of months later, found out, or did some experiments, they found that it really wasn't pure water after all. They found that if you put water in these capillary tubes, it actually, the material, the silica from the capillary tubes actually dissolves in the water. Not much of it, a trace of it, but still the Russians had argued that this was pure water, and this group found that it was not pure at all. Actually, it was contaminated by silica. And so they said it was a silica gel, and therefore no big deal about these interesting properties. And then what made matters worse is there was another group, I believe this was an Australian group, and they put salt in the water. And when they put the salt in the water and measured the absorption spectra, the same as the Russians had done, they got practically identical results. And so they said, well, the Russians must have been sweating into their water when they did their experiments. And it was really embarrassing for the Soviets. And a couple of years later, Deryagin himself drove the nails into his own coffin, if you will, by publishing a paper saying that all of his critics were right. They screwed up, they made a mistake, forget polywater, forget everything that we found. So that seemed to be the end of the story, and the end of the story is that, well, if the greatest scientists, physical chemists in all of Russia could screw up so badly, then mere mortal scientists had better stay away from water, because they're going to screw up even worse than that, or there's that potential. And it seems that that's the end of the story, but it's not the end of the story. I've heard now from 3 different people who were close to Deryagan that despite the fact that he wrote that paper, he was actually forced to write that paper because, it's an embarrassment to the Soviet government, and it's easier to place the onus on that particular scientist than on Soviet science. So he basically took full responsibility, and I suppose his alternative was, who knows what, maybe Siberia or something like this. So they professed that until the day he died, he was absolutely sure that he was right.
Wow.
But yeah, it's an interesting story. It could make a good movie.
We have a better way in the U.S. We simply make it impossible for researchers to work if they say something that's not popular. So
I know well about that phenomenon. No, it's not that different, but I think the consequences are maybe more dire for him.
Versus change of career. Yeah, you got to point that.
Maybe a gulag. I'm not sure, but certainly he would not have been the famous scientist that he and respected that he remains today. But as I said, mere mortal scientists were encouraged to stay away from the subject of water. So then, water began. The science of water began its recovery. And then a second debacle took place. This one was in France, and the French are equally proud of their science. They have biological scientists, mathematicians, and many distinguished French scientists. And then along came this guy Jacques Benveniste, who was a famous immunologist, a really high-level guy with a lab of 50 people. And he was doing some experiments on cells. They're white blood cells called basophils. And he would pour some, perhaps you know the story, he would pour some antibodies on the cells. And when the cells received the antibodies, they got activated and they secreted something. I believe it was histamine. And they were studying this as part of their immunological research. And some guy came along. He said, I can dilute those antibodies again and again and again and again, just as the homeopaths do. And I could dilute it so many times that essentially there are no molecules of no antibodies left, just water, essentially water that had been in contact with the antibodies. And I can pour that on the cells and get the same response. He said, impossible. But, being an intellectual and open-minded guy, he said, okay, there's a corner of the laboratory there. Nobody's working. You can show us what you're doing, and, we'll see what goes on.
The reason I'm laughing, sorry to interrupt you there, is that I think 80% of people out there go, that's impossible, therefore it can't happen, therefore we're not going to test it. Right? And they just ignore a potentially really interesting thing. So I love it. Okay, in this experiment, you had a real scientist who said, well, if it's real, prove it. Okay, and what happened next? I got to know.
Well, what happened next is that pretty soon everybody in the lab was hovering over this guy to see his results because apparently it worked. He could do those dilutions. He did it exactly the same as the homeopaths do it. You dilute, say, 1 to 10, and then you shake it. They call it succussion. And then they dilute again, and they shake it, and so on, go down the line. And so he produced it. And Jacques, who I knew personally, he died about 10 years ago, was, of course, so curious about this and found that this experiment was so interesting. He had no interest whatsoever in homeopathy, but he was really interested in what these dilutions could do and the response. So he decided to publish a paper on this. So he sends the manuscript to Nature. Sir John Maddox, the editor of Nature, received it, and he said, no way. He said, if you're right, everybody else is wrong. And I refuse to believe that everybody else is wrong. Sorry, we won't publish your paper. So Jacques, being a determined scientist and believing in his results, though he didn't really understand the mechanism. And when I chatted with him, he said, I'm just an immunologist. I'm not a physicist or a physical chemist, so I don't understand the mechanism. And he was honest enough to say that. But as you said, there was something going on there and something that needed explanation. So he thought, okay, Nature rejects it. I'm going to ask my colleagues in different countries to repeat our experiments exactly as we did, and if they get the same result, we'll publish together. They got the same result. They submitted the manuscript to Nature. The response was the same. And by the way, this story is written in several books, books with, you might say, different tilts. Some tilt in favor of the scientists doing the experiments, and one or two in favor of Nature, of the editor of Nature, who they believe had some good points. And pretty soon what happened is that the homeopaths realized that this famous scientist was basically able to figure out, to demonstrate that what they do clinically actually has some kind of physical basis. And pretty soon Nature, whose headquarters are across the channel in London, heard about this. It was published in the newspapers and such. Their protests had to do something, had to respond in some way. And Jacques, when I was visiting his lab, he said, "Oh yeah, Maddox, he telephoned me on that telephone right there." And he said, "I'll make a deal with you." So what was the deal? The deal was, we'll publish your manuscript next week, next edition, if you allow a group of peers to come to Paris and watch you do the experiment, look over your shoulders, and then we'll report back to our readers in Nature. So Jacques thought, well, this makes total sense. We can get our paper published, and we'll demonstrate to them that this is real. So they published the paper with a disclaimer saying, we're not really sure about this, but in fairness, quote unquote, in fairness, we're publishing this paper. So the next step was that Maddox got together his committee of peers to go and visit. And the committee consisted of three people. One was Maddox, who was himself, who was trained as a physicist. He never quite made it to his PhD. He became a journalist and worked his way up to being the editor of Nature, a rather distinguished position. And for the other two peers, one of them was the amazing Randy, a magician, perhaps thought of by many as the world's greatest magician, with wonderful capability of figuring out the tricks of other magicians. And the third one was a guy named Walter Stewart from NIH, who is in, you might say, the fraud department. Right. It's called the division or department of scientific integrity. And what this division does is to investigate claims that appear to be outrageous, and they go and they look and hear the evidence from both sides, and they come to a conclusion as to whether the scientists' findings are real or actually fraudulent. So this was the committee. This was not exactly a committee of peers. It was a biological experiment. It was you might say, a commando committee designed to figure out what the trick was, because they were sure that it was a trick. So they came to Paris. They came to the laboratory, and on the first day, the technician who does the experiments regularly did the experiments, and the results turned out exactly as they had published. The second day, the technician did the experiments again, and each of the tubes or the vials was coded by the committee. Only they could decode it. And when they decoded, they actually found that the result was, again, just as they had predicted. And the third day, the dilutions were done by Walter Stewart, the NIH fellow, and the result didn't turn out that way. And I should say that in their paper, they mentioned that the result doesn't always turn out the way they suggested, but statistically, it was overwhelming the percentage of times that they get the result that they claimed, that there was no question, but they didn't know exactly why. Sometimes it didn't work. Anyway, it didn't work, and so the committee of peers huddled, and they decided that, well, when the French do the dilutions, it works, and when the visiting committee does the dilution, it doesn't work, and therefore it must be a fraud. They couldn't figure out what the fraud was.
Kind of like the French paradox, right?
Yeah. Well, okay. Yeah. So they and this was the end of Benvenist's career, because the headlines in Nature was that this is a delusion, a trick of some sort. And of course, everybody wanted to believe it was a trick because it's unimaginable that water has the capacity to store information. And the implication of this was that it did, because this water had been exposed to the original antibody molecules, and it must somehow have acquired information from those molecules. Otherwise, the experiment wouldn't have worked. And Jacques told me that it was a real mistake to call it water memory, because for most people, it's inconceivable that water can remember something. It turns out that, I should say that a couple of things about Jacques Benveniste, a heroic guy, and his experiments have been repeated. They were first repeated by people who said they couldn't get the same result, and that was published in Nature, happily, for the Nature people, because they wanted to be vindicated. But the response from Jacques Benveniste and crew is that, if you really sincerely want to repeat some of these experiments and you can't get the same result, the first thing you do is call them and say, what am I doing wrong, if you're sincere about it. And so he argued that these people they didn't follow the same protocol, and therefore it's unlikely that they would have gotten the same result. However, I found out afterward that this was maybe 5 years afterward. I met a guy at a review in Japan, and this is a high-level French scientist who was an advisor either to the prime minister or the president or something, and he said he was on the committee that made sure that Benveniste never got a grant again, despite the fact that his work was confirmed, and he gave me the papers that confirmed his result. Now it's been confirmed many times since then, but he said that the reason that they discontinued his funds is not that they didn't believe his work, but it was an embarrassment for French scientists, for French science. It's quite analogous to the Russian debacle that took place, and so French science was vindicated, and Jacques Benveniste was guilty, and he became a scientific joke. You're having trouble remembering, drink some water, and water memory will restore. And when I began my work, I was discouraged from beginning this work because first you have Boris Deryagin, and then you have Jacques Benveniste, and these two debacles. So many people have been really fearful, many scientists, of immersing themselves in water. So it's a long story, and it's an interesting story, and that's why water is not a discipline. We have disciplines of nanotechnology and genomics and such, and you'd think that water would be important, but there's almost no field. We tried to nucleate one. We have annual meetings that I organize. It's called the annual conference on the physics, chemistry, and biology of water. And it attracts really interesting people who are doing groundbreaking experiments. A very exciting meeting to attend. It's during the past 3 years or so, we hold it in Bulgaria, which may sound like a strange place, but Bulgaria has healing waters, and maybe I think it's something like 40% of all those in Europe are in Bulgaria.
Wow!
So it's an appropriate place for a water conference.
So I have a random question related to that.
Please.
I drink San Pellegrino, even though it's owned by a big mean water company, Nestle. But San Pellegrino or Saint Pellegrino healing waters, I think it's better. Also, I like that it's bottled in glass. Is there something special about, I don't want to call it that one brand, but about drinking bottled mineral water, things like that? Or am I just deceiving myself, but at least it's BPA free?
The answer is yes.
Both?
Well, I can't profess that you're deceiving yourself. I think, let me say that I've seen evidence that some waters have healing capacity. And I'll just tell you about one example. On the other hand, there's so many waters that you can buy either in the supermarket or online. There must be dozens of them online, and they all profess to have healing powers. There's one that I came across. I got a phone call 4 years ago from a guy, and he told me that he worked in a famous laboratory. The laboratory shut down, and he took the apparatus they had, and he created water for his own family, drinking water. And he told me they haven't had the flu or anything for 2 years since they started drinking that. And so, my reaction was, okay, big deal, maybe many reasons why your family hasn't had the flu for a couple of years. But then he told me that the next door neighbor who knew about this water that they were drinking, the neighbor knew of a friend who was on dialysis, irreversible kidney pathology. And she wanted to drink the water. So he managed to give her the water. And he told me, he said that after 30 days of drinking the water, she went from irreversible pathology to no pathology.
Oops.
My reaction was, I don't believe you. Actually, I did believe him, but so he sent me the hospital records, which confirmed that was the case. So I invited him to our conference to present his work, because obviously, if you have water that can reverse irreversible kidney pathology, that's quite amazing. And by that time, he had more evidence, and one of the people at the conference went to visit him, and with the prospect perhaps of providing this on a larger scale for humanity. He called me. He told me that the business arrangement didn't work out. However, he saw the hospital records, and he interviewed every patient who this guy had claimed the pathology was reversed. He said it's true. So I became really impressed, and he actually is selling this water right now. And so this is one case where it appears that there's real evidence. You might call it anecdotal evidence, because there have been no clinical trials, but it looks promising.
So just to point that out for the kind of the skeptic crowd, anecdotal evidence is still evidence, right? It's just not as strong.
Absolutely.
As right?
It's right. It's statistically speaking, the point is there may be other people who drink the water and with no result. So and I guess a proper way would be to do an extensive series of tests and a blind or double blind test and see what works and what doesn't work. Actually, we proposed that because there are so many waters, and I think some of them look promising, and needs to be done by an independent agent, someone who understands about water. To do that requires, $4 or $5 million to do it properly, to test patients, to test animals with tumors or animals with irreversible organ disease like liver pathology or kidney pathology. Otherwise, it's difficult to tell because you go on the internet and you find these waters and the very sincere sounding claim that water can really help reverse pathology. You just don't know to trust it or not trust it.
There's a really rough thing here because I run a company, and when there are rules right now where the government says, look, you may not make a medical claim about something that's not a drug. So if you have a water that makes people young again, that actually works, and it works even in a bunch of trials, if you make that claim, they'll step in and shut your company down and say, look, you're making a claim about water's not a drug, therefore it can't do this, which is anti-science on its face, but it's true for every food item out there. So these poor, I've met a few that probably, maybe even some of the same people, where they're working on these amazing water machines, and you drink the water and you're like, well, I can feel there's something in here, and I'm pretty sure this isn't placebo. Just like, if you got caffeinated or decaf coffee, it's pretty hard for that placebo effect because there's something happened from the caffeine.
Yeah.
So you drink it, okay, I don't know if I can finish this because I'm kind of buzzing. But then if they go out there and they start saying this stuff works, then as soon as they hit a level of commercial success, they'll get shut down. It happens over and over to my great frustration. And I don't really know how to get around that, because what we need is a little bit of freedom of speech for businesses to say, we don't know, but we're pretty sure, and here's our evidence, and you can decide for yourself because it's unlikely to cause harm. But until we get that right in this country, which we don't have right now, do you think that any of these water companies have a chance of sort of seeing the light of day?
Well, they have seen the light of day, and some of them are more successful than others. But as you say, they can't claim what might actually be the case. There's one that's different. Perhaps you know about the Kangen water.
What do you think of that?
In Japan. So, I have no comment.
Okay.
I don't know. Sometimes we drink it, but I got to tell you that in Japan, they did do clinical trials of that, and as a result of the clinical trials, there's a whole bunch of evidence. As a result of the clinical trials, if you have any kind of gastrointestinal problem in Japan, from your mouth down all the way to your anus, they put you on this water, and the government pays for it. Governments don't pay for something that that doesn't have efficacy. So they've done enough trials on that. But I mean, still there are some people who claim there are some long-term effects that maybe are negative. I'm not sure about that. But I just want to point out that in Japan, the clinical trials worked, and people are put on that water. It's actually very simple. You just put the water through two electrodes in the machine. One's negative, one's positive, and you drink the one that passes through the negative electrode, which has a high pH, and the stuff that comes out through the positive electrode has low pH, and if you try to drink it, you spit it out immediately. It tastes like something like highly chlorinated water. It kills bacteria, but it's certainly not good for you. I think our research shows that the negative charge is really important for health, and is a different issue, but it's not something that is a kind of a mainstream kind of idea, but it goes back to the water, the kind of water that this fourth phase that we discovered, which is negatively charged. That's one of the features of this water, and it's the kind of water that fills your cells. So,
does a Kangen machine make water like the fourth phase of water?
Not sure. Okay. We tried testing that kind of water, and using the test that we usually employ, it didn't show it. However, in the laboratory, when we did experiments putting the negative electrode in the water, we actually did find this kind of fourth phase water that we discovered. So the answer is I'm not sure if it does or doesn't. But for sure, it has negative charge. And so, your cells, this kind of water that we're talking about, the fourth phase water, forms next to hydrophilic, water-loving surfaces, and the cell is just filled with water-loving surfaces. All the proteins and other macromolecules are charged on the surface, and so the water that sits next to those surfaces should be easy water, or we call it the EZ, exclusion zone, fourth phase. It's just different terminology for the same thing. So this stuff is your cells are replete with this kind of water. It's not ordinary H2O that's in your cells, and physiologists know that cells have net negative charge, and it's been there have been some hypotheses as to for 50 or 60 years as to why the cell has a negative charge, but since we've found that the water that populates the cell has the negative charge, we kind of understand that one possible reason for the cell's negative charge is because it has this kind of negatively charged water. You have a sack with some negatively charged stuff in, and the sack is going to have a net negative charge, and we've measured that. And so if your cells don't have enough of this water, then your cells are going to be less negatively charged. And if your cells have a full complement of this stuff, they're going to have more negative charge. So we've come to kind of a hypothesis that the more negative charge that you have in your body, the healthier you're going to be.
Now that's different than the pH of your cells, though, right? Because
well, yes and no. So we think of pH. We think of pH as a concentration of hydrogen ions, or OH minus. But some of the experiments that we've been doing indicate that when you have low pH, that is a lot of protons, you have net positive charge. And when you have more OH minus groups, you have excess negative charge. So it's not that that every solution is neutral. it's possible, we're studying this right now, it's possible that as a rule, when you have something that's acidic, that is an abundance of protons, that you actually have that this solution that you hold in the beaker actually has net positive charge. It's not neutral. Chemists like to invoke the principle of electroneutrality. Everything should be neutral, but we know everything is not neutral because you can actually measure. You can take two beakers with one substance and another substance, and you can actually measure a potential difference between this, and you can get current flow from one to the other. And so it seems possible, if not likely, that liquids can sustain charge. And we made measurements of people. And so you are negatively charged. I'm negatively charged too, but I think you're more negatively charged because you're healthier than I am, or at least you don't have as much gray hair.
There you go.
So, and that's why, there's this idea about earthing yourself or grounding yourself. You take a walk on the beach, take off your shoes, and you feel good after 10 or 20 minutes or so of doing that. And the people who have studied this understand that what you're doing is you're actually soaking up negative charge from the Earth. The Earth has a net negative charge. This is another fact that is not widely known, but among the Russians and in other countries 50 or 60 years ago, it was common knowledge, but we've forgotten that. And so when you connect yourself to the Earth, you sop up this negative charge, and you feel better. You feel healthier. So the research has shown that. So I just want to make that point that anything you can do, practically anything you can do to gain negative charge should, in theory, be good for your health. Antioxidants are one of those because oxidation is loss of negativity, and so antioxidation means you don't lose that negativity, and that negativity is really important. The body actually tries its best to get rid of positive charge. If you think about it, every time you go to the toilet and pee, the pH of that is low. It's and so you're getting rid of protons, getting rid of positive charge. Every time you exhale, you're getting rid of CO2 and water, which is carbonic acid, getting rid of positive charge. When you sweat, it's similar. You sweat. The sweat actually has low pH. And a colleague of mine was actually measuring his body's charge and took a dump and found out afterward that he got more negative. And so apparently you're losing positive charge that way too. This needs to be studied, of course, in greater depth, but it's a kind of principle that comes out.
I've definitely been sleeping with one type of earthing or another for 8 years now, I think 9 years, and talking about it
Really?
as one of the hacks that you can do. But I used to weigh 300 pounds. I had chronic health problems as a child, arthritis at 14, and all sorts of stuff that shouldn't have been, including basically mitochondrial poisoning, as far as I can tell, from living in a water-damaged building where you get airborne mycotoxins that inhibit mitochondrial respiration. And I've since recovered pretty darn dramatically from all that kind of stuff.
It seems so.
And one of the things that helped the most was ozone therapy, which you actually use ozone gas, small doses of it rectally, which has lots and lots of free electrons in it, right?
Yeah. Yeah, you figured out another way to do that.
Yeah, and they actually do it intravenously as well. And I've also done a lot of electrical current stuff over my body that seems to have played a major role, as well as I had an alkaline water machine starting in '96. I bought one before Kangen came out, I think. But it actually just caused diarrhea because it turns off stomach acid where you kind of need acid. So it turns out for me, I'm already too alkaline. So I had a weird situation where I was actually not making energy well in the cells, yet I was almost on hyperalkaline, which didn't make sense, but it was because something was inhibiting respiration. So you go through all that. A lot of people, we call that chronic fatigue syndrome, fibromyalgia, Lyme disease, all that stuff.
Yeah. Yeah.
What does your discovery have to say about like those situations, those people who are running around running at half strength? Like, do they need more easy water? Do they need more grounding? Like I mean, you're studying bioengineering, some of the most interesting stuff I can think of. If everything sucked in your life because you just never had enough energy and nothing seemed to be working right, what would you do with water in order to turn things back on?
Well, okay. There are a couple of things. Besides drinking the right water, which is not so clear which one is the right water, light is also one really powerful agent.
Yes.
And so why is light a powerful agent? Well, so this water that we're talking about, this fourth phase water, is built by light. If you start with water and you want to create, you start with ordinary water and you want to create this fourth phase of water, light is the agent, is the energy that does it, and especially infrared light. So infrared light is all over. You can't get rid of it. It's if you turn off all the lights in the room and shut the shades and whip out your infrared camera, you can get a beautiful image. It's sort of like these night cameras. Yeah. Everything generates infrared at night, no visible light, but lots of infrared so you can get an image. So it's all over, and it's actually literally free energy. It's not the kind of free energy that we learn about in our chemistry class, but it's literally free for the taking. It's there, which means that this water, this fourth phase water, is also there. However, if you're sick, there's a fairly good chance that you're deficient in this easy water. There are various scientific reasons that we reach this conclusion that maybe are beyond going into here, but I can just say that your cells, it's the proteins in your cells that act. They fold in certain ways, and that makes the cell work. And the usual environment for folding is that each protein is surrounded by fourth phase water. And if you don't have enough of it, then your proteins are not surrounded by their usual milieu, and they can't do what they ordinarily do. And so your cell is sick. It's not actually functioning. So one possibility is that you want to build up this easy water in your cells. And the way to do it is one way to do it is to expose yourself to infrared light. I just came from Russia. I was there a few days ago, and the way they do it is we call it sauna, and they call it banya. It's the same sort of thing. You go into a room, and it's either with water or without water, humid or not humid. With infrared, it's at a very high temperature, and so you soak up this infrared. And when you come out 20 or 30 minutes later, you feel like $1 million, or rubles, if you like. and so why is that? Well, one thought is that this is purely psychological, and maybe some of it is. But our experiments show that if you add infrared light, infrared energy, you build easy fourth phase water, and the same thing happens inside your body. Your body soaks up this infrared energy because water in your body likes to absorb that kind of energy. And from our experiments, we know that builds easy water. So one possibility, a hypothesis, is that by sitting in the sauna or the banya, the reason you feel good is that your cells, particularly the cells that had been deficient in easy water to begin with, the water builds up, and you have then a full complement of easy water. And so if your muscles were aching, a reason why they might have been aching is that they're basically dehydrated. They for whatever reason, don't have enough of this water. They get rehydrated with it. So therefore, and it could be the same thing happens in your brain. You're feeling depressed. Your cells are not, your brain cells, your neurons are not functioning optimally. You want to get them to function the way they should function. So you add the infrared, it builds up the water, and then your cells begin functioning normally. So it's a kind of general effect this infrared...
Sorry to interrupt. Is a campfire good enough? I mean, is a radiant heater good enough?
That needs to be studied. People are using different wavelengths of light. Sitting in front of a campfire, usually you feel good.
Yeah, exactly.
The same kind of, right. I hadn't thought about that, but perhaps it is good. I know that in Asia and some countries like in Korea, they have different stones, different crystals that they heat depending on what your issue is and what your problem is. And this needs to be studied as well, but it seems to be quite effective. So, if you have a stomach problem, you subject yourself to one set of wavelengths of infrared. And if you have a liver problem, perhaps another set of wavelengths. So I just want to say that it's not just the sauna or the banya. It's actually light therapy is used for many issues, from depression to skin disease, and more light therapy is becoming routine, and it's expanding rapidly.
I've had different colored lasers for doing light therapy. Low level laser therapy became low level light therapy. Going back about 15 years with profound results on my own, like muscle relaxation and speed of healing and things that are almost unexplainable. I think we're discovering it now. And your book, I think, explains some of the reasons why that might work, because I can't tell you all the reasons it works. There's some things about nitric oxide that are interesting, depending on if it's a red light or whatever else. But I can tell you, you put an infrared LED or a red LED or some cases blue, but not usually. You put those on and something very tangible happens. And as a scientist-minded person, you're like, okay, I don't know why, but I know if I do A, then B usually happens. I'm going to take advantage of the effect while I discover why.
Absolutely, absolutely, sure. You need to. I just was exposed recently to another kind of therapy. It's actually using ultraviolet light.
Oh, neat.
So this is done.
Intravenous?
It's a local.
Or?
Yeah, actually intravenous.
I do that too.
You stick. You've done
absolutely.
That. Yeah. How did you feel?
It makes you feel amazing. And so why do you think that might work? I know there's a vitamin D effect that's little known, but what did you experience? I'm really interested.
I haven't had it done myself. I just saw the machine that's used to demonstrate it, but I think it works because this is a bit of a longer story, but I think that if you look at the blood flow that occurs in very small capillaries, I think it's different from what we presume. And I found this out actually in Russia. I started my career studying the dynamics of the cardiovascular system, the heart developing pressure and pumping into the arteries and arterioles and such. And I thought for sure that we had all the answers and that I could explain practically anything. People who develop models almost uniformly think that, and I guess I was one of those. And when I was in Russia, I go there fairly frequently. I admire the Russian research. These are people who really think. I was at Moscow University, and some friends of my friend sat down with me, and they told me there's a real problem, and the problem is that you have capillaries, and for young adults, healthy adults, the capillaries are 3 or 4 micrometers in diameter, but the red blood cells that need to pass through are almost twice the diameter. So it looks like Mother Nature screwed up, and there's a plumbing problem here. It's sort of like, you go to the toilet and the stuff that needs to go through can't go through, and you need the plunger to, you know what I'm talking about. So it's kind of similar, because the question is that they raise is, well, I mean, how do you get those red blood cells to pass through something that's narrower? And if you look at videos showing this, you can see that the red blood cells actually, they kind of scrunch down in order to get through. But that scrunching requires energy, you see. And what they pointed out is that if the heart were really responsible for driving those red blood cells through those tiny capillaries, the amount of pressure that they would need to develop is something like 1 million times the pressure that the heart actually develops. So something else is going on. There needs to be some kind of assist to this. And I think the assist comes from light. And the reason I think so is that we can put a tube in water and like a straw, just put it in the water, lay it down horizontally, and flow goes through that tube automatically and endlessly. It just keeps flowing. And we discovered that about 3 years ago, and we have a few papers on it.
Sounds like a perpetual motion machine. I mean, someone should take away your license.
Yeah, it sounds like it.
Right? I mean, you can't talk about these things. Tell me more. I'm so interested.
No. It sounds like a perpetual motion machine. And of course, it does. Usually what you need is pressure to drive fluid through a pipe. And if you have no energy, then, but we know about the energy because water absorbs energy from the environment, the infrared energy, for example, any kind of light energy. Some wavelengths are absorbed more than others. So the water is receiving energy all the time and transducing that energy, converting it into other kind of energy. And so we pinpointed the energy is coming from light. And you could look at the flow going through the tube, the water flowing through the tube. We put little particles in the water so we can actually visualize microscopically. You can see the flow going through. And we turn up the light. And we were able to get up to 5 times faster flow just by turning up the light intensity. That's all.
Wow.
And then turn it back down, it slows down.
In darkness, there's no effect.
Yes and no, because the infrared light is dark light. I mean, it's not in the visible wavelength range. So turning off the lights in the room removes the visible wavelengths. But since it's mostly beyond the visible, actually, some of it is infrared, but also ultraviolet light has an effect as well, and we found, in fact, that ultraviolet light, it was really effective in speeding up the flow through the tube. So in the laboratory, we turn on the light, we get flow through a narrow tube. Why shouldn't the same happen inside your body? You turn up the light, or the light that's being absorbed, maybe actually driving those red blood cells through those narrow tubes, just as we saw in the laboratory. And we're now doing some experiments to test this idea.
Does it matter UVA, UVB, UVC?
Well, we're testing that right
now. Oh, cool.
Now.
I want to see your research. I expose myself every morning for about 10 minutes because I live on Vancouver Island up near where you are in Seattle. There's not enough sun here, so every morning for 10 minutes I get my ultraviolet radiation in the form of a sun lamp. I'm usually on a call with one of the members of my team, and I'm sort of like naked standing in front of a light. But fortunately, it's not a video call, so it's all good. But I'm hopeful that may be beneficial for this stuff, but I don't know. But I know for other things like vitamin D and sulfation of vitamin D, it's probably good. But is it a good practice? Yeah. Would you recommend it or not?
I can't say. All I can say is that it probably is. But we haven't done trials on that.
So by the way,
I'm not sure.
Thank you for that answer. The average scientist, when we say, well, I know you don't know, but if you had to bet, they're so hesitant. I don't really want to bet until I've done a double-blind study. And you're like, and you're willing to say probably is actually a really courageous thing. So thank you for that. Because
well, at the risk of criticism from my colleagues, I mean, it's great to have hypotheses, and then you get somewhere.
As long as you qualify it, I think you're being very scientific. I had a chance to ask Craig Venter, like, given everything you know about the human genome and all this incredible research, like, what should I do today based on your best possible guess? I said, or should we just have pizza and beer and figure it out? And he goes, let's talk about it over pizza and beer. And I'm like, so I'm going to pull my hair out because he's such a luminary. But that scientific thing says, until I'm really sure, I'm not going to choose a direction. And what I want to do is I want to live to 180 years old. I'm going to pick a direction, because if I don't pick a direction, I'm probably going to go the wrong way. And I might pick the wrong direction, but at least I tried. And
you might pick the right direction. 180, that would be impressive.
I'm working on it.
Good luck. Hope you get there.
Do you do any work with the piezoelectric effects of cell membranes by any chance?
No. Why do you ask?
I have a machine downstairs that's made out of a cockpit from a fighter jet. And it takes you to 22,000 feet elevation, drops you to sea level, back to 22,000 in rapid succession, which pumps all of your cell membranes, and has a bizarre piezoelectric, like it generates electricity on the cell membrane. And it's a really cool thing, and it's a little known effect, but I just thought of anyone I've ever spoken to on Bulletproof Radio that might be an effect that you'd come across.
How do you know it's the membrane?
There's actually two studies. I'll send them to you afterwards, talking about a cell membrane piezoelectric effect about little lipid spheres on the surface of the cell membrane, that they themselves are piezoelectric apart from like bone piezoelectricity and things like that. So I was blown away to see it, and you certainly feel an effect from it, but it might be a nitric oxide effect, not anything more, and there appears to be a stem cell effect. But it's also one of those things where you can't really say what it does, even if you think you know, because then you'd be selling drugs. So it's a machine that makes you feel good, right?
Yeah. Well, there are mechano-electrical effects for sure, because, if you have easy water sitting next to ordinary water, one is more dense than the other. That is, the easy water is denser than the bulk water. If you squeeze it, put pressure on it, then the tendency is to go toward the more dense of the two. And so we found experimentally that if we did that, if we apply pressure, we get more easy water. And easy water is negatively charged. So it means you apply force and you get charge out of that. So it's essentially a piezoelectric effect. And that's why I asked you how sure you were that it was a membrane effect. Many scientists attribute almost everything in the cell to
even though the membrane
doesn't
really exist when you look at what happens when you strip the membrane and the inside of the cell still works. So the membrane isn't what we think it is. I'm with you there.
I think that's true. The membrane is overrated.
Yes. Now, okay, let's assume that I have a couple $1,000. And I actually live on an organic farm, doing my best to keep everything working in my body. And I can do whatever I want to my water filtration system. I already have activated charcoal. I use a well that's not polluted. I run it through a UV filter and various polishing things. It's absolutely neutral and from a pH perspective. Do I need to install a big bank of infrared LEDs in a clear tube? Do I need to install electrodes? Like, what do I do to basically shower in easy water that drips out of the faucet like syrup every day? Like what should I do here?
Again, I'm not sure, but I can certainly speculate or hypothesize. Sure. I think light is really important. Spend your $2,000 putting light into it. And if you ask me which wavelengths, I'm not sure. I would say that probably we found that infrared light at roughly 3,000 nanometer wavelength is very good for building easy water, especially if you have a little bit of salt, if you have minerals in the water, which you probably do. And you because what happens is that the easy water, the fourth phase water, builds around the minerals themselves, and so if you add light of the right wavelength, you get more easy water. And I think that waters, at least the evidence so far, is that if you drink water that contains easy water, it's likely to be good for you because that's the kind of water that's inside your cells. Yeah. So you're basically refurbishing water inside your cells. So I guess that's probably what I would do. But again, I'm speculating.
Thank you for labeling it as speculation. I totally understand it's speculation, and everyone listening, if you go out and you buy this and it does the opposite of what you expected it to do, it could happen, right? This isn't double blind.
It could happen, yeah. But this is, you really put your finger on something that's terribly important. Water is so important for our health. It's central, but there's almost no funded research on water. If you try to get money from the National Institutes of Health, if you want to study a drug, it's fine. It's no problem, as you pointed out earlier. But if you want to study water, this is something that they almost never heard of. Yeah. And so there are no funds available to do that. And with your influence, perhaps you could change that. It's really, really important to study water.
I'm really intrigued. I do work with the X Prize Foundation, the guys who did a $10 million grant to basically turn on private space exploration, and it worked. Yeah. And there are a bunch more X Prizes like that. So this makes me think that maybe we need to do an X Prize with Hero X around funding some fundamental research. Let me keep my mind working on that because this does deserve a lot of attention. Have you looked at the O16 versus O18 DDW, like deuterium depleted water? Is that anything that's been in your research?
No, we haven't done it, but I know that there are some scientists who are studying that. And you probably know more about that than I do.
It seems
positive effect.
I'm thinking about getting something that makes DDW water, which is a sizable investment, but I want to live to 180. I just don't know if it's worth it, right?
What about drinking the Hunza water? Do you know about the Hunza?
I know about the Hunza people, but I'm not sure about Hunza water.
Henry Coanda, who was a Nobel laureate studying fluids, went to visit the Hunza to find out why they lived to not 180 as far as I know, but certainly 110, 120. They have babies at age 90.
I'm going to race Ray Kurzweil. That's my goal.
Well, so he found out that it's the water that it's full of minerals. It's actually thick with minerals, and the tourists who go there drink the water. I'm told that they actually filter the water for them because those people won't drink that water that's kind of thick with minerals. So I'm not sure they get the full benefit of it. But I'm not sure if you know Patrick Flanagan, who. Yeah, he studied that and he produced a product.
Miracle crystal stuff, the little droplets you put in. Yeah, I used to use that.
Yeah, apparently mimics what the Hunza have used, and again, that might be another good approach. I must mention one more since we're talking about health, and that is juicing. Probably you do that too.
Yeah, I like to juice my maple trees. I drink the sap that comes out before you concentrate it into syrup. That's basically pure easy water, as far as I could tell.
Yeah, it must have a lot of EZ, but I'm talking about the sort of more standard way of taking vegetables and maybe some fruits. Yeah, or kale. It doesn't taste great, but you kind of get used to it and begin to like it. And, so what you're doing, what you're drinking is essentially cell water, right? Because it's the water that you squeeze out is the water that's inside the cells of the plants. And the physicians I've spoken to, you might call them alternative and complementary medicine. Many of them use it, and the patient comes in, and it doesn't matter what the problem is, but including some of the ones you mentioned, fibromyalgia and kind of vague symptoms. And it seems that almost always drinking that stuff for a few months is of great help. And as I said, I think the reason it helps is that you're adding cell water to the water that may be deficient in your own cell. Which reminds me of the famous book that you probably know about, the one that's You're Not Sick, You're Thirsty.
Oh, right.
You know that book? Yeah, and that also is anecdotal evidence, but powerful anecdotal evidence by this Iranian physician who became a political prisoner because he was a supporter of the Shah, and when the Shah was deposed, he was thrown in prison. So he was a physician, and so he was the one who had to treat all the other political prisoners, and all he had available was water. And so finally he wrote the book that described his experiences not only in prison treating patients, but when he emerged from prison and continued his studies. I found myself really, really impressed by the sincerity of this book, which, by the way, his son, who I met by chance, told me sold more than 7 million copies. Yeah, really popular. It's cheap. You can buy it on Amazon. It's very impressive. One chapter deals, for example, with diabetes, another with heart disease. And he tells stories about his patients who came in and he said, just drink a lot of water. And they got better just by drinking a lot of water.
I had a weird experience back when I was living, it turns out, in a mold damaged, water damaged building. So I was getting daily exposure that was causing immune inflammation. I did a 24-hour urine challenge. You had to collect all your urine for 24 hours. I collected 7 liters of urine.
7 liters?
Yeah.
Wow.
Okay. Granted, I was probably 280 pounds at the time, but I wasn't trying to drink extra water. Partly I was because I knew if I drink more water, I'll be healthier. I was always thirsty, but it was like the water wouldn't stick in my body. Like no matter how much I drank, I was always thirsty. Is this a water structuring issue, or is this like my kidneys are over toxic? What was going on? Do you have any idea?
Well, it could be a water structuring. Okay. Yeah, I mean, so the ability to hydrate may depend on the type of water, and I bet it does. And again, we have a theory as to why this might be. The cells are negatively charged, and if you exposed water that has charge, so-called dipolar water, where you have plus at one end, minus at the other, It should be absorbed more quickly by this negatively charged cell, because what happens is that, you've got a blob of negative charge, and then you have a dipole sitting here with a plus and minus. If this is negative, the plus will orient closest and get pulled in.
Okay.
And the fourth phase water is definitely charge separated. It's a dipole. It has huge amounts of negative at one end, positive at the other. So it should be sucked in by the cell more quickly. Again, this needs testing.
Of course.
Just a hypothesis.
We're in the land of theories now. Are you at all concerned about these LED lights that make no infrared whatsoever but have lots of the blue spectrum?
Yeah, I am, because I heard some talk at one of the conferences about so-called light pollution.
Yeah.
And in some cities, it's light all night, and the blue light is stimulatory, and I think it's stimulatory because I think the energy from the light creates more of this separates charge, and the separated charge gives you energy, so it keeps you energized just when you want to go to sleep, and so I think this is problematic.
I switched all of the exterior lighting on my house. So I'm in the country, like I see no lights from my house, and I switched them all from whatever they were, halogen for the most part, to red LEDs that are sea turtle friendly and all. And the night I did that, the owls started hanging out right next to the house.
Oh,
Before
wow.
they would not be anywhere near. There's 2 or 3 species that are nearby. And it was profound what the effect on wildlife was, not to mention my own. I can walk outside and see the stars and things like that.
Fantastic. Yeah, this is a growing issue, along with electromagnetic pollution. It's a serious issue because it's really not clear what cell phones and such. It's sort of clear, some people have done studies, and the studies, I have a colleague in Seattle who's been studying this most of his career, and he says, the studies that are funded by the cell phone companies, 95% of them report no problem. But the studies that are funded by foundations or other organizations, not the cell phone companies, 95% of them report serious problems. So I actually thought I was the only person on the face of the earth who decided to own no cell phone, but I met another one yesterday. And so apparently there were at least 2 of us without cell phones.
Is this because of the effect of EMFs on water or on cellular biology, mitochondrial activation? Like what's your specific concern there?
Well, the colleague of mine had studied DNA breaks that occur from, and so it's not the kind of thing that you want to happen. We haven't yet had the wherewithal to study the effects of different wavelengths on water, but since water absorbs many of these wavelengths, you put your water in the microwave oven and it heats up, and that's because these wavelengths are absorbed by the water. But we don't know what each of those wavelengths actually does to our body, and this needs to be studied. It's really important to do this because, well, for obvious reasons.
Because life depends on it?
Yeah, because life depends on it. It's terribly important.
There's one more question I want to ask you before we come up on the end of the show, and that is, 2 more questions, including the final question. But the other one is, I know that when you drop the temperature of water, it's easier for easy water to form. I do cryotherapy with liquid nitrogen. So I stand in air that's chilled to 260 degrees below zero. So the very outer centimeter or so of my skin gets a real strong signal about how cold it is. It doesn't freeze, but it drops the temperature pretty darn far. Am I doing something cellular with easy water, do you think? I know this is the land of speculation here. Or is this more about signaling for essentially more calories burned and brown fat activation and things like that?
Well, the latter is certainly possible. I couldn't comment, but I think what you're doing is you're generating a lot of infrared energy in the core of your body. All the metabolic reactions do that. And when you stand outside in the cold, then you have a huge gradient of temperature from the inside to the outside. So the infrared energy that's generated in your body goes through the body to the periphery and out toward the cold. It's passing through your tissues. And when infrared energy passes through your tissues, it builds easy water. And so Yeah, so I think that might be what's going on.
That's cool. I've never heard that, and that makes so much sense.
Well, it's interesting to have a conversation because some of these issues, stimulate both of us to thinking.
Right.
There's nothing like thinking.
My unusual path has led me to believe that there's quite often 5 or 6 different effects that stack on each other when you really feel something work. And you can hypothesize there's these ones. And so much of Western science is around looking for single variables. But almost every problem that's ever been meaningful to me has been a multivariate problem, which makes them very hard to study.
It's really hard, yeah. That's the reason for some basic science. If you start at the fundamental level and figure out what's going on, then you can apply it to the body, and you'll know that at least that's perhaps one of the factors that's involved.
Yeah, it might be why it works, but we still can measure that it works. So let's keep looking for all the reasons, right? And that's what gets me up in the morning. It's so exciting. Speaking of getting up in the morning, I want to ask you the question I've asked every guest on the show.
Oh.
And this is, if someone came to you tomorrow and said, based on everything you've experienced in your life, not just your science, but certainly including that, if I want to kick more ass at everything I do, like I want to be better at everything, what are the 3 most important pieces of advice you have for me? What would you say?
Oh. Okay. I think motivation is one, but the question is how you develop motivation. People without motivation are really not going to get very far. Curiosity and audacity. The world around tends to be pretty conservative. We feel comfortable with what we know. If we're bombarded with something, as you said earlier, that we can't explain, we have a tendency to dismiss that because if we can't explain it, it must not be true.
Yeah.
And this is a very serious issue, and I think it afflicts many scientists who will reflexively dismiss ideas because if it's a good idea, somebody would have discovered it before. So don't bother us with this idea.
Right.
And that is really a critical one. It's critical. It's not just for science, but for other realms and other disciplines too. It's having the audacity to go ahead and follow your belief system with some reservation. You have to listen and hear the facts. But is one of the reasons I feel really strongly about this. Is one of the reasons why we've created an organization called the Institute for Venture Science, IVS. The website is ivsci.org. We haven't seen during the past few decades very many scientific revolutions or breakthroughs. 100 years ago, there were many of them. You can go back and they're familiar names, Einstein and Max Planck and Pasteur, and there were so many that Curie that occurred. And the question is, at that time, there was very little money for science. Now there's a lot of money. We all complain that there's not enough, and it's true. But we have a lot of money compared to then, and yet it's really hard if you try to put your finger on fundamental scientific breakthroughs, not technological. There have been lots of those, iPhones and such, but fundamental scientific breakthroughs that are at the same level as the discovery of the periodic table or the splitting of the atom or the structure of DNA, which was, I think, 60-odd years ago. Mm-hmm. You can't find them. It's really hard. Revolutions, not promised revolutions, but revolutions that have changed the world. And I think one of the reasons is that it's difficult for scientists with fresh ideas to gain traction. And the reason is the one that we discussed, that, if that's true, people would have discovered it 100 years ago. And so we created this institute to change that. And the idea is that it works on 2 principles. And one is that if you propose that the Earth is round and everybody around you knows that the Earth is flat, if you put a proposal into a standard granting agency, You'll be reviewed by the experts, naturally, the experts in the field. Those are the flat earth people. Your chances of getting money to pursue what you want are vanishingly small. And by some quirk, if you happen to get the money and you study and you obtain even more evidence that the earth is round, you'll be labeled as a crackpot because many people are threatened by that. All the flat earth people don't want you to be correct because many of them are more interested in their careers than they are in finding the truth, shall we say. And maintaining their career means they have to be right. And if you're right with round earth, they're wrong. And so they're no longer the kingpins in the field. That's very threatening to people. It's a human issue. And so we get around that by actually taking round earth ideas like that, ideas that we, not the experts, people who can understand what you're talking about, but don't have the skin in the game to want to dismiss your idea. So we accept your idea, we fund you, and then we look for other groups around the world who have a similar vision that you have, that the earth may be round. And then next year, we fund them. And next year at the annual meeting of the Shape of the Earth Society, suddenly there are maybe 10 or 12 groups, each one using a different method, demonstrating that the earth is round. And you can't ignore that anymore. And so this, we think, is the key to breakthrough science, revolution, if you will, funding multiple groups, developing a critical mass. And we think that this is going to be able to restore revolutionary science the way it was 100 years ago.
Well, I am more than ever motivated to introduce you into the Hero X Foundation and the X Prize people. What they managed to do is put a little prize purse on it. So instead of just writing grants, which is a possible thing, the team that wins a sizable purse, even if it's only $500,000. That's still a huge amount of money compared to the $10 million they use for a space flight. But when you have that element of competition, it seems to move things forward in a really cool way.
Could be.
Interesting.
Yeah.
Okay.
Yeah, I mean, anything you can do. The world really needs fresh thinking. There are many ideas I come across. I'm familiar with many different scientific fields. People come to me because they sense an open mind and they like to tell me about what they're doing. Some of the stuff, frankly, I think is flaky. Other is amazing. I mean, truly amazing. There's a guy who I met the past couple of years who was actually able to cure cancer with his hands.
Wow.
His name is Bill Bankston, and he's done experiments on mice with tumors. It's a mammary tumor. It's 100% fatal. And he puts his hands around the mouse that has been injected with the tumor and has already developed a large mass. And he runs through in his mind a kind of a list of positive emotional experiences he's had in his life, and he runs through again and again and again, and his cure rate is 100%. This is the kind of stuff people don't know about this, and of course, a lot of people will feel threatened by it because it's a multi-billion-dollar business, if you will. Not only the pharmaceuticals, but all the researchers who are studying, chemotherapy and other kinds of measures to combat cancer. So this is entirely different, and it's not easy for him to get research money to pursue this. So it's just one example of many out there, many really promising ideas that need to gain traction to see if they're really as worthwhile as some of them appear to be. It's going to change the world.
It absolutely will change the world, and there are some people who appear to have pretty strange abilities, and there's a reflex among the skeptic community, which is actually a surprisingly small percentage of people, but a very vocal percentage of people.
Yes.
But it's probably 2 to 5% of people where everything is glass half empty. But the real scientists out there who are actually doing real evidence-based medicine versus what is only double-blind study-based medicine, which isn't real at all in terms of real evidence. There's many kinds of evidence. But when you look at something like that, any true scientist go, that sounds hard to believe, but if it's true, it's one of the most important things ever. We need to see if it's true. Whereas we have this response, which is, bullshit. That cannot be. Therefore, anyone who even talks about it is a con artist and a quack. And
pseudoscience.
Yeah, and that kind of reflexive stuff, it's just fundamentalism. It's no different than ISIS. And it's really bad for the world. And I will not have that. It is just not okay. So
well, good for you.
Let's look at that stuff. Let's figure it out. And some of it is totally self-deception. That's great. Let's figure it out. But if you don't apply science to figuring that out and you apply dogma to figuring it out, you're a jerk. And I'm totally happy to call you that. I'll get off my soapbox there, but you got me going.
Yeah. No, I believe me, I hear you. And if you're well connected and you know some people of means who want to return something to the world, this is the Institute for Venture Science is a perfect place to do it. We've just launched, and we're looking for donors who want to see changes in the world in their own lifetime. Have a front row seat where they can see things happening.
So, Jerry,
this is a good
I think I know a group of extremely financially successful, hundreds of millions to $1 billion kind of success people who'd be really interested in your work. And I will be doing some back channel introductions and things like that.
Oh, that's great. Thank you very much.
Some of my coaching clients have been very successful. And so let me just drop a few little comments in the right places and maybe something great will happen. If not, I can make a few intros to people who can maybe just move the initiative forward. So this is important work, and thank you for doing it, and thank you for your audacity. That's exactly the right word. I really appreciate your work, and I'm grateful that you're on the show today.
Well, thank you for having me. It was really fun.
Well, likewise.
Appreciate it.
Have a beautiful day.
You too. Take care.
If you enjoyed today's show, and let's face it, how could you not enjoy the show? Gerald Pollack he spent his whole life doing this amazing, amazing work. And when you read his books, they're technical, but you realize there's something happening that science did not know about. And he's just had the tenacity to dig in, and he's discovered some fundamental things that I believe have a really good chance of changing the way we understand biology and changing the world. So if you enjoyed the show like that, I would love it if you supported the show. And there's something in line with what we talked about today, and it is the ZenTech screen protector. This is something you slap on your computer, you slap it on your phone, you do it one time, and it blocks some of that blue light we talked about that comes without infrared, which lowers the amount of stress on the cell membranes in your eyes, and it lowers the effect of blue light on the body because it filters out some of the blue light. This is a pretty cool thing, and it's a one-time thing you do. Just go to bulletproof.com and search for ZenTech, and you can pick one of these things up, and you'll probably feel the difference in your sleep. And if you don't, you can always send it back. Have a beautiful day. I'm so excited about this interview. I'm super charged by it. I'm going to go get some infrared lights and stick them all over my water supply. Have a great day.